Today our last section is on Bernoulli's equation. Now these are simply equations that can be reduced to linear differential equations by some substitution. So these are equations that can be reduced to linear differential equations by substitution. So that means at first glance, when you look at them, they are not they are not linear, so you cannot rewrite them in the form that we require. But if you were to make a substitution, then changing the variables, you can rewrite it so that it is in fact linear. And then once you've made the substitution and you can see that it is now linear, you will then go ahead and solve it the way we solve linear differential equations. So we'll look at some examples of this. First one, we have a 2y dy dx plus 1 over x times y squared is equal to 2. Okay, so here we know that a linear differential equation must look like this. We have dy dx plus p of x times y, and this is equal to q of x. So this is what a linear differential equation must look like. And then we can think, okay, what if we just divide everything by 2y? Then we will have the dy dx, we will have p of x, and then this will be y, because y squared and y cancel, but then on this side we will have a y as well. So it is not going to be linear, because with your linear differential equation, you need this to be dy dx and this to be the only y in the equation. But we can actually make a substitution here, and the substitution we make is we say let z equal to y squared, and then this means that dz dx, this is 2y dy dx. So this is the substitution that we make. So what you should always take note of is here you will have a function, or you rewrite it. So here you have the function, and then this is the derivative. So you see I have y squared, the derivative is 2y, or at least a scalar multiple of that derivative. Then we can make this substitution, and then when we do that, 2y dy dx is just dz dx, and then I have 1 over x times z, and this is equal to 2. And now when I look at it, this is actually linear, because I have my dz dx like I have here. I have my function of x, that's p of x. I have the variable that I differentiated x with respect to here, and then on the other side I have a function of x only. There's no z on this side. And then we would solve this by finding the integration factor, and we say the integration factor is just the e to the power of the integral of this function here. So our integration factor is e to the power of 1 over x dx and this is e to the power of ln of x, which is x. So then we multiply everything by x, so you have x, x, and x over there. So that will give us x dz dx plus 1 over x times x is 1, you have z, and this is equal to 2x. And then from here, this is where you condense this using the product rule. So see, I have x here, the derivative of x is 1. I have z here, the derivative of z is dz dx. So I can just write this as x times z prime. This is equal to 2x. And then to get rid of the prime, I integrate both sides. We have xz is equal to 2x dx. So xz, and this is x squared plus c. And then remember, there was no z in the question, so we have to write z in terms of y. So we have x y squared is equal to x squared plus c. Okay, so that is our solution. So again, Bernoulli's equation, they are not linear to begin with, but by making a substitution, you can rewrite it so that it does become linear. Okay, we have 3y squared dy dx plus 1 over x times y cubed is equal to 2. So again, what you're looking for is this function here in terms of y and the derivative of y. Okay, so 3y squared, its derivative is y cubed, its derivative is 3y squared. So I can just make the substitution. We say z is equal to y to the power of 3, and then dz dx. This is 3y squared dy dx. And then making the substitution, I have z dz dx plus 1 over x times z. This is equal to 2. And then we have reduced it to a linear differential equation. And then we just need our integration factor, and then we will be able to solve it. So again, our integration factor is e to the power of the integral of 1 over x dx, which is e to the power of ln of x, which is x. So I multiply everything with x. I have dz dx, there's an x, dz dx plus z is equal to 2x. And then this becomes xz prime is 2x, and then we integrate both sides. We have xz, the integral of 2x dx, xz is x squared plus c, and then this is y to the power of 3 x squared plus c. With 3 minus 1 over y squared dy dx plus 1 over x times 1 over y is equal to 2. So again, you look at this function here, when I differentiate it in terms of y, I get negative 1 over y squared. So I can make z equal to this. So we say z is equal to 1 over y. This means that dz dx is negative 1 over y squared dy dx. And then we substitute. We have dz dx plus 1 over x times z, or just z over x. This is equal to 2. And again, now it is linear. We just need our integration factor, e to the power of the integral of 1 over x dx, e to the power of ln of x, which is x. So multiply everything by x. We have x dz dx plus z is equal to 2x. So this is x times z prime. This is 2x. And then we integrate. Get xz is equal to 2x dx. Xz is equal to x squared plus c. And then z is 1 over y. So we have x over y is equal to x squared plus c. Number 4, we have cos y dy dx plus 1 over x sine y is equal to 2. Okay, then again here we have sine y. The derivative of sine y is cos y. So we can just say z is equal to sine y, and therefore dz dx is cos y times dy dx. So substituting, I have dz dx plus z over x is equal to 2. And then again, our integration factor, e to the power of the integral of 1 over x dx, e to the power of ln of x, which is x. And then when you multiply everything with x, you have x dz dx plus z is equal to 2x. And then on the left hand side, you can compress that using the product rule. So we have x times z prime. This is equal to 2x. And then to get rid of the prime, we integrate. So xz is equal to the integral of 2x dx. Xz is equal to x squared plus c. So we have x sine x is equal to x squared plus c. Okay, so that is pretty much how we solve all our Bernoulli equations. Then look at some more. This is number 4, number 5. We have dy dx plus y is equal to x y cubed. Okay, so here what we need is we need a function of x on this side only. There shouldn't be a y. So what we should do is first divide everything by our y to the power of 3. So I have 1 over y to the power of 3 plus 1 over dy dx plus 1 over y squared. This is equal to x. Okay, and then we check if we have this function here, is this the derivative? The answer is yes. The only thing is it needs a constant. So we can say z is equal to 1 over y squared. And then this means that dz dx, this is equal to negative 2 over y to the power of 3. And from there, we can say that 1 over y to the power of 3 is equal to negative a half. Okay, from there, we can say that negative a half dz dx, this is equal to 1 over y cubed dy dx. Okay, so now we can make the substitution. This is negative a half dz dx. This is z, and this one remains as x alone. So we have negative a half dz dx plus z, and this is equal to x. So as it is, it's still not in linear form because we need the coefficient of our derivative here to be 1. So that's easy to fix because this is a constant. We just multiply by negative 2 throughout. So we have dz dx minus 2z is equal to minus 2x. So now it is in linear form. We can find our integration factor. So our r, this is e to the power of minus 2 dx, which is e to the power of minus 2x. Then multiply everything by the integration factor, e to the power of minus 2x dz dx minus 2e to the power of minus 2x times z. This is minus 2x e to the power of minus 2x. Okay, and then on this side here, we can rewrite this as z e to the power of minus 2x prime, and on the other side we have minus 2x e to the power of minus 2x. Then to get rid of the prime here, we integrate on both sides. So we can say that z e to the power of minus 2x is equal to the integral of minus 2x e to the power of minus 2x dx. Okay, to integrate this, we need to use by parts. So we have x 1 0, and then we are going to integrate e to the power of minus 2x, is negative e to the power of half minus a half e to the power of minus 2x. Then we have positive 1 over 4 e to the power of minus 2x. Then we draw our arrows like that. Okay, so the first one will be positive x times that, then negative 1 times that, and then the last one will be the integral of 0, which is just a constant. So we have z times e to the power of minus 2x. This is equal to, remember this negative 2 here, we took it out. So we have negative 2, And then our first term, we said it's x times this. So it is minus x over 2e to the power of minus 2x, then minus 1 over 4 e to the power of minus 2x, and then we add our constant. The negative 2 can multiply inside. We have z e to the power of minus 2x. This is x e to the power of minus 2x. And then we have plus a half e to the power of minus 2x, and then we add our constant. Okay, so remember z was not there in the question originally, so we need to replace that in terms of y. So z was 1 over y squared. So we have e of minus 2x over y squared. This is x e to the power of minus 2x plus a half e to the power of minus 2x plus c. So you can divide everything by e to the power of minus 2x, that is fine, but this is also okay. Number 6, we have sec squared y. Just going to write y prime plus sec x tan y is equal to cos x. Okay, so here we have tan y. The derivative of tan y is sec squared y, so that is the derivative. So we can make our substitution. So z is equal to tan y. Then z prime, this is sec squared y times y prime. And then we substitute. So we have z prime plus sec x times z. This is equal to cos x. Okay, so it's in linear form. We just need our r, e to the power of the integral of sec x dx, which is e to the power of ln of sec x plus tan x. Again, an integral that we have done several times. I was surprised in the test people couldn't integrate this when we've integrated that so many times. And then this is equal to sec x plus tan x. Okay, so now that we have our integration factor, we will multiply everything by the integration factor, and then this will give us sec x plus tan x z prime plus z. So z is being multiplied, it's here, z sec x times this, so we get sec squared x sec x tan x times z. So we have z sec squared x plus sec x tan x, and then on the other side we have cos x times sec x plus tan x. Remember, sec x is 1 over cos x, so sec times cos is 1, and then tan is sine over cos, So cos times tan is sine. So this is 1 plus sine x. Okay, then we look at what we have here. This we can just condense to z multiplied by sec x plus tan x prime, which is 1 plus sine x. And then to get rid of the prime, we integrate on both sides. So we have z sec x plus tan x. It's the integral of 1 plus dx is z sec x. This is x plus or minus cos rather. And then rewrite z in terms of x. It's in terms of y. We have tan y sec x plus tan x. This is x minus cos x plus c. Okay, and if we look at a few of the exercises, a few of the questions in the exercise, there's only like 7, so but I don't want to do all of them. Let's start. We have exercise 5.9. Okay, let's start with number 1. We did that one. Let's start with number 2. We have x y cubed dy dx. This is x ln of x minus y to the power of 4. Okay, so first thing you want only x or only a function of x on the right hand side. So we have x y cubed dy dx plus y to the power of 4 is equal to x ln of x. And then here you don't want any terms that involve x, so you divide everything by that. So we have y to the power of 3 dy dx plus y to the power of 4 over x is equal to ln of x. And then if I look at this function y to the power of 4, the derivative is a constant multiple of y to the power of 3, so I need a 4 here, but I can still make the substitution. So we say z is equal to y to the power of 4. This means that z prime is equal to 4y to the power of 3 y prime. Yeah, somebody's saying something. Okay, and then divide by 4 on both sides. So we have 1 over 4 z prime. This is equal to y cubed y prime. Then we substitute. We have 1 over 4 z prime plus z over x. This is equal to ln of x. So it is in linear form now, and we find our integration factor, which is e to the power of ln of x, which is x. Then multiply everything by x. Sorry, before that, it's not in linear form. There's a 4 here, so we need to take it away from there. So we have z prime plus 4z over x is equal to 4 ln of x. And now we can work out our integration factor. E to the power of 4 ln of x, which is x to the power of 4. Okay, now we can multiply by x to the power of 4 throughout. So we have x to the power of 4 z prime plus 4x cubed times z. This is 4 4x to the power of 4 ln of x. Okay, and then this one we write it as z times x to the power of 4 prime. This is 4x to the power of 4 ln of x. Okay, then integrate. We have z x to the power of 4 is 4 times the integral of x to the power of 4 ln of x dx. And this one to integrate, we will let u equal to ln of x, and then this means that du is 1 over x. Here dv is x to the power of 4 dx. Don't forget the dv and the dx here, the dx there. And then we have v is equal to x to the power of 5 divided by 5. Okay, then we substitute and integrate. So we have z x to the power of 4. This is 4 multiplied by u times v. So this is x to the power of 5. X to the power of 5 over 5 ln of x, and then we minus the integral of v times du. So it's x over 5, x to the power of 5 over 5 multiplied by 1 over x dx. So z x to the power of 4. This is 4x to the power of 5 over 5 ln of x. Then minus 4 the integral of this is 4 over 5 outside, and then we have x to the power of 4 dx. So this is z x to the power of 4. This is 4x to the power of 5 over 5 ln of x minus 4x to the power of 5 over 25 plus our constant of integration. Okay, so now it is integrated. We just need to rewrite z in terms of y. So this will give us y to the power of 4, x to the power of 4. So it's 4 over 5, x to the power of 5, ln of x minus 4x to the power of 5 over 25 plus c. Okay, then you can multiply everything by 25 to get rid of the denominators, so it looks nicer, I guess. Okay, then number 3. Okay, let's look at number 3. We have y prime plus y cos x ln of y is equal to y cos of x. So remember, first thing is on the right hand side, we only want functions of x, so we need to divide everything by this y. So then we will have y prime over y plus cos x ln of y is equal to cos x. And then we have ln of y, the derivative of ln of y is 1 over y, so we can make the substitution. So we have z is equal to ln of y, and then z prime, this is 1 over y times y prime, so it's just y prime over y. So z prime plus z cos x is equal to cos x. And then we need our integration factor. E to the power of sine x, then multiply everything by the integration factor. We have e to the power of sine x z prime plus z e to the power of sine x times cos x. This is e to the power of sine x times cos x. Okay, then on the left hand side, we can rewrite this as z times e to the power of sine x prime. This is e to the power of sine x cos x. Okay, then to get rid of the prime, we just need to integrate on both sides. So we have z e to the power of sine x is equal to the integral of e to the power of sine x times cos x dx. Okay, and then this is just a matter of substitution because the derivative of sine x is cos x. So we have z e to the power of sine x. This is equal to e to the power of sine x plus c. And then rewrite z in terms of y. So we have ln of y e to the power of sine x is equal to e to the power of sine x plus our constant of integration. Okay, so here just multiplying. Okay, in number 4, we have dy is equal to x times 1 plus y squared, 1 plus tan inverse of y dx. Okay, so we try and rewrite it in standard form. So we have dy dx, this is equal to x 1 plus y squared, and then multiplied by 1 plus tan inverse of y. Okay, everything can go to one side, so we have dy dx minus x 1 plus y squared 1 plus tan inverse of y. This is equal to 0. Okay, then we can divide by 1 plus y squared. So we have dy dx times 1 over 1 plus y squared minus x 1 plus tan inverse of y. This is equal to 0. Okay, and now we look, the derivative of this is that one, so we can say z is equal to this. So we have z is equal to 1 plus tan inverse of y, and this means that z prime is y prime over 1 plus y squared, which is exactly what we have over there. And then we make our substitution. We have z prime minus xz. This is equal to 0. Okay, then we need our integration factor. This is e integral of minus x dx, which is e to the power of minus x squared over 2, and multiply everything by the integration factor. We have z prime e to the power of minus x squared over 2, then minus x z e to the power of minus x squared over 2, and this is equal to 0. And then the left hand side, we can write that as z multiplied by e to the power of minus x squared over 2 prime, and this is equal to 0. And then integrating on both sides, we have z e to the power of minus x squared over 2. This is equal to a constant, and then we write z in terms of y. We have 1 plus tan inverse of y, and we have e to the power of minus x squared over 2. This is equal to c. So we can divide by e to the power of minus x squared over 2 on both sides. 1 plus tan inverse of y is equal to c times e to the power of minus x squared over 2. And then that is your solution. Okay, so the rest of the questions in the exercise are for you to try. They are not particularly difficult if you remember the procedure of how it is we actually do it. And I always say it is good to practice. Okay, and then that will bring us to the end of this course, Math 2. So remember, the test is sometime next week. I'll let you know the date as soon as I get it, but this one will not be an open book test. So use this time between now and the test to study and do as many questions as possible.